Alright, so complex numbers are a lot like stuff that we've already seen. So like they're in a two-dimensional plane, similar to the XY plane, except this time, the axes are real and imaginary axes. So what that means is complex numbers are usually represented in forms such as a plus bi, where a is the real part and bi is the imaginary part. But b right here, b is going to be a real number. Adding I to it, because I is imaginary, is going to make the entire thing imaginary. So the imaginary component of this complex number, which is usually denoted as z, is going to just be b. So when we plot this on our graph, and this plane is called the Argan plane, okay? And our regular rectangular coordinates are called the Cartesian plane. That's our xy. But this is the Argan plane. So when we plot this, so let's say we have a complex number and it's 3 plus 4i. Well, on the real axis, we go over 3, 1, 2, 3, and on the imaginary axis, we go up 4. So 1, 2, 3, 4, and we plot the number right here, and this point right here would be 3 plus 4i in the Argan plane. And so another common thing is to ask for the magnitude of a complex number. And so if we have 3 plus 4i, the magnitude of that is really simple to calculate when you think about it graphically. Because you might be like, well, how do you calculate the magnitude of something that's imaginary? Well, if you look at this on the Argan plane, the magnitude is just the length of it, right? So if we start from the origin, which we always do, and go up to that point and make a sort of position vector. Okay, actually, never mind. This length right here is the hypotenuse of a triangle with height 4 and base 3. Okay, right? So if this is a right triangle, well, we can use our Pythagorean triples, or just use Pythagorean theorem to calculate that the magnitude of this complex number is 5. So you can think of it a lot like vectors in that way. And so the way you would calculate the magnitude of z would be, which is denoted like this, would be to take the square root of your components. You could, technically, I guess it is taking, yeah, it's just this. This is your magnitude. And it's not bi squared, because when you square b, you're going to have b squared, but when you square I, you're going to have negative b, and we're not subtracting b squared, we're just adding them. So you only have to worry about the actual real and imaginary parts for calculating the magnitude. Oh, another thing worth mentioning that you'll commonly see is the complex conjugate. And what the complex conjugate is it's denoted by z with this sort of line over it, and it's a minus bi. So the complex conjugate of this number, which, well, let's just call this number u, the complex conjugate, actually usually, let's do w, because that's conventional. So the complex conjugate of w would be 3 minus 4i, which is graphed at 3 on the real axis, and then 1, 2, 3, 4 minus 4i. So this is w right here. Actually, this is the conjugate of w, and this is w. So as you can see, the conjugate of something is the coordinate itself reflected over the x-axis, right? Just because we're switching the y-coordinate. So you can think of it as the coordinates going from 3, 4 to 3, negative 4 on the rectangular plane, right? Just because we're changing the sign of the y-coordinate. So like I mentioned, this is the real and this is the imaginary. So sometimes you'll see them ask for the real component of z or something. Let's say the real component of w. So if they ask for the real of w, if you see this, don't be weirded out. It's just going to be 3, right? Because that is the real component of w. I think this is as kind of a function that you stick in your complex number and it spits out a real number, but like whatever component it is, whether real or imaginary. This will always be real, of course, but it spits out a real number. But the thing with these functions, like sometimes they'll ask for the imaginary component of, let's say, the conjugate of w is this right here is, the part that makes it complex. But this is not the answer, because this is only asking for you to have the -4, right? You don't include the I. These two only are ever only going to be real numbers. So it would just be -4, because the -4 is the complex. It's the imaginary part of the conjugate of w. All right. I hope that makes sense. So moving on. Actually, one more thing. A common question that I've seen on tests, and that kind of confuses people for, I feel like no reason, is when they ask you to find the area. Let's say this question asks you to find the area enclosed by the magnitude of z, which equals 5. And people are like, what does that mean? Well, this is why I always like to think about stuff graphically, because if you have an area enclosed by every complex number, and you think about it as the area enclosed by every complex number with a magnitude of 5, you might be like, what? Well, how am I supposed to know and graph this out? But really, it's so simple, because if you try to calculate it, like a squared plus b squared equals 5, and the square root of that equals 5, that's hard. But if you think about it graphically, and you think about all these numbers having a magnitude of 5, well, you realize that just makes a circle of radius 5 centered at the origin. So the area would just be 5 squared times pi. So it would just be 25 pi. And so, as you can see, it's not complicated at all. Okay, so now let's move on to adding and subtracting complex numbers. So everything about, besides the nuances of, real and imaginary, everything about adding complex numbers is so similar to adding vectors, and the same with subtraction. So I'll go over it anyways, but most of this should probably be a review. And I'm sure you can figure it out. So let's say we have the complex numbers 4 plus 2i and negative 6 plus just normal I. So if we were to add these, let's do this. Just if we were to add these, literally all we would do is add their real components and then add their imaginary components. So that gives us -2 plus 3i. Because these are the same number, but as it is with vectors, x and y components behaving separately, with imaginary numbers, our real and our imaginary components are independent of each other, right? We can just add up the real components and then add up the imaginary components. And you'll be able to see this graphically. So let's say we have our vector. Let me do this in 2 colors. We have a vector 4 plus 2i, so 4 plus 2i. That's right here. Sorry, not a vector, a complex number. And then, but we can represent it as a position vector, which is a vector that just indicates a point's position. And then we have the numbers -6 plus I, which is here, -6 plus I. And I feel like the reason vectors, one of them, I don't feel any bad about using vectors to represent complex numbers or anything, and the reason they go so well together is because with complex numbers we're always concerned about magnitudes, and our coordinates for them are so much like vector coordinates, the way we add them, the way we subtract. So I think they just go really well together. But yeah, so we have -4 plus 2i, -6 plus I. Oh, sorry, 4 plus 2. Okay, perfect. And now we want to add these vectors. Oh god, hopefully this works. Okay, so let's add, it doesn't matter which one we add to the other. We can either add this one up here, or we can add this one over there. And so let's just add this one over here. Now, when we do that, we can see that the x component, when it was from -6, shifts right 4, and then it shifts up, we're at 1, it shifts up 2 as well, or at least it should. These are not evenly spaced, but you can see what I mean by it goes up 2. So it'll take us to this new coordinate of 2, 3i. Or if we did this the other way around, and we took this vector and we added it here, we can see that it goes left 1, 2, 3, 4, 5, 6, and it goes up 1, or at least it should go up 1. So yeah, let's just move it down. Now it kind of goes up 1. But as you can see, adding these two are it's very easy. It's very simple, and it does show that our coordinate becomes -2 plus 3i. So now let's subtract them. Okay, so let's subtract these two numbers. And again, we can do this with our components separately. And if we have 4 plus 2i, and we're subtracting -6 plus I, and this time, you know, the order of course does matter because it's subtraction. So we end up with 10 plus I. And so what we do for this one is we can think of it as adding the negative vector. So we have 4 plus 2i, and we want to subtract this. So what we can do is we can take the negative of this vector, which we get by rotating it 180 degrees. Oh no. Whatever, it's fine. Maybe I can better tell what it's... Uh-oh. We have a... Oh, hopefully this was right. 1, 2, 3, 4. Yeah, okay. We take the negative of this vector, and we add it to this one. So it goes here. And oh no, bad choice of numbers. Now it's... Oh well. So, as you can see, the y-coordinate, I mean the imaginary component at least, is right. So it goes down 1. We're subtracting 1 from the imaginary component. And from the real component, we're actually subtracting -6. So we're adding 6. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow, it's right on the coordinate of 10 and then I. So that's what subtracting imaginary numbers looks like. And now multiplying imaginary numbers is a little different. And this is where it's not like vectors at all, because with vectors we have our dot product and our cross product, and this is just like normal multiplication. So let's say we have 4 plus 2i and then -6 plus I. When you multiply these complex numbers, we're just going to be distributing and, you know, multiplying. So we have 4 times -6 is 24, plus 4 times I, which is 4i. Then we have 2i times -6, so -12i. And then we have 2i times I. So I times I gives us -1, and so this becomes -2. And so we'll always have 2, whenever we do this, we'll have 2 reals and 2 imaginaries, unless stuff cancels out. So we're left with -26, and then this is -8i. And so this would be the product of these two complex numbers. And one other thing is that let's just look at what a complex number times its complex conjugate would be, alright? And let's just do this in general form. So a plus bi times a minus bi, let me just title this multiplying. Oops. So this will give us a squared, right? And then a minus bi, so plus or minus abi. And then we add bi times a, so plus abi. And then we have minus bi squared, which is just minus b squared I squared, which is just minus negative b squared. So this becomes plus b squared, right? All of this. And so these middle terms cancel out, and that just leaves us with a squared plus b squared. So a complex number times its conjugate is just going to be the magnitude of that number squared, right? Because the magnitude is the square root of a squared plus b squared. So when we square that, that's going to give us the complex number times its conjugate. And that's because the plus bi and the minus bi, you know, the middle terms will always cancel out like this. And so that's why when we divide complex numbers, we want to always utilize this so we can get rid of imaginary numbers in the denominator, right? We don't want that. When we rationalize Like, for example, we rationalize to get rid of square roots in the denominator. Typically, we don't want those in the denominator, and we don't want imaginary numbers in the denominator either. And so we always have to rationalize by utilizing conjugates, or at least in most cases. So let's use, our same numbers that we've been using, and so dividing. Let's do 4 plus 2i divided by, what was it, negative 6 plus I? I believe so. Yeah, negative 6 plus I. So this, it is a number, but we always want to rationalize this. So if we want to get rid of this imaginary component in the denominator, as we did here, now it's just a squared plus b squared with no i's up here. What we can do is we can multiply both the top and bottom by the complex conjugate of negative 6 plus I. Because when we do that, we're just multiplying it by 1, right? Which doesn't do anything. So that's why we're allowed to do this. So we have negative 6 minus I at the top, negative 6 minus I at the bottom. And so when we multiply this together at the bottom, it's just going to be a squared plus b squared, which is 36 plus 1. Plus 1. And then on the top, it's just going to be 4 times negative 6, so negative 24. I think we already multiplied this out, actually. So it's negative 26, as you can see up here. It's just negative 26 minus 8i. Negative 26 minus 8i. And this is not simplify nice. I just chose random numbers, but sometimes they actually do simplify nice. You'd be surprised. Over 37, which you can write like this, but a lot of times you should write them as negative 26 over 37 minus 8 over 37i. But both ways are correct, and you will probably, see them both ways when you're doing problems. Alright, so that was just an introduction to complex numbers, and hopefully it helped.